Good morning, esteemed judges, fellow innovators. My name is Prasad Siddhant, team leader of G14, and today I am thrilled to walk you through the creation of the Neural Clinical Data Mesh backend, a comprehensive system I built from scratch to transform clinical trial data management. We'll cover the major files, the step by step development process, the core logic, and the techniques that make these projects work. Let's dive in. When I embarked on the project, I had a clear mission to create a patient centric knowledge graph that integrates disparate clinical trial data sources, automates quality checks with AI, and provide conversational insights, all while ensuring full auditability and compliance. The backend is the engine of the system, handling data ingestion, AI orchestration, and API serving. I started with Python as the foundation, leveraging its ecosystem for data science and web development. No frameworks were chosen lightly. Each decision was driven by the need for scalability, security, and real world applicability. The first step was establishing a solid foundation. I created backend config settings.py to centralize all configuration. This file uses Pydantic base settings to load environment variables securely, including database credentials and API keys and model endpoints. It ensures the app runs in different environments, development, testing, and production without hard coding sensitive data. The logic here is simple but critical. Validate inputs at startup to prevent runtime errors. Next, I defined the data schemas. In the backend dataset schemas.py file. Using Python data classes, I created structured representations for each of the 9 datasets like CPID, EDC metrics, and SAE dashboards. This enforces type safety and make data validation straightforward. For example, a patient schemas include fields like subject ID and study ID with validators to check for required formats. This step was essential for data integrity. Every ingested record must match these schemas, preventing corruption in the graph database. Step 2. Building the data pipeline, ingestion and graph construction. With the foundation in place, I moved to data ingestion. The core file here is ingestion graph ingestion.py. This script processes Excel SX files from the QC anonymized study files directory using pandas for efficient loading. The logic transforms flat data into Neo4j graph nodes and relationships. Patients become nodes, visit becomes connected entities, and metrics like DQI are calculated on the fly. The step-by-step process is load and validate each file against schemas, create or update nodes in Neo4j using cipher queries, establish relationships such as patient has visit site, log ingestion stats for monitoring. I used batch processing to handle large datasets without memory issue and implemented idempotency. Rerunning ingestion is safe. This technique ensures the graph is always up to date and queryable. Now I would like to take you to a visit to our database information which contains nodes around 1,60,848 with audit entry, coding issues, EDRRI issues, inactivated form, lab issue, missing pages, patient, SAE, site, study, visit, and a relationship of total 1,61,136 which belongs to site, has adverse event, has coding issue, has EDRR issue, has inactivated form, has lab issue, has missing page, has visit, site in study, etc. You can see one of the knowledge graph which is formed here which gives the information about the coding issue, inactivated form, patients, SAE, sites, etc. And the relationship that which belongs to which site, has adverse event, has coding issue, has inactivated form. You can click on the each node to get details about that particular node with the ID which it's contained. Here amendment manager, record inactivated, adverse event form 69, record position 3, site ID 3, subject ID 6. Similarly, we have other knowledge graphs uh, for the inactivated forms, missing pages. You can click on the node and see the visit level, days missing, page name, site ID, etc. Here you can see the lab issue with the patient, missing lab name, lab category, date, site, subject ID, test description, etc. Also with the number of sites and the site in study, region, country, site, study. You can get all the information in the knowledge graph which has been created for the agents to properly analyze the data without any major issues. USA, America, sites, etc. These are the nodes for the patients, site and study number. Let me zoom into this graph so that a better overview can be seen. So this is our knowledge graph. Now moving forward, now by seeing the knowledge graph formed in our Neo4j database, we confirm that we are going right in our journey. Now moving forward, step 3, that is the implementation of the AI agents, automation and intelligence. The heart of the system lies in the AI agents, starting with the backend agents base.py. Here I defined an abstract base agent class with common methods like audit log for compliance and calculate context for personalized responses. Each agent inherits this, ensuring consistency in every response, which is REX, risk evaluation expert, is one of the agent which scans for the data quality issues. Logic includes calculating metrics like the data quality index using formulas from our instructions and flagging anomalies with confidence scores. Next agent is the codex coding agent, which automates medical term mapping. It queries the graph for uncoded terms, uses Longcat AI for suggestions and applies changes only above a 95% confidence threshold, reducing manual work by 80%. And the next agent is the LIA agent, that is site liaison agent. Here, which monitor compliance. It analyzes visit projection and sends context-aware emails, escalating only critical issues to avoid alert fatigue. Here is the base agent. You can see the code. The technique here is agent-based architecture. Each agents run asynchronously, logging every action for audit trials. I integrated custom AI clients like Longcat client to handle model interactions securely. Adding conversational AI, which is for RAG, using the RAG technology, that is retrieval augmentation and generation. Adding conversational AI, retrieval augmented generation. Conversational capabilities are powered by conversational engine.py. The file orchestrates intent parsing, query execution, and response generation. The logic uses RAG parse user queries. Show missing visits is the example into structured intents, retrieve data via cipher, and generate narratives with citation. The key techniques: intent classification with regex and keyword matching, graph queries for deterministic retrieval, no hallucinations, traceability via backend conversational rag traceability.py. Here is the rag traceability.py file, which comprehensive internal citation mapping, deterministic regeneration capability, audit logging for user query, retrieved data and generated text, data lineage tracking for every generated output, which logs every retrieval and generation for compliance. I build this iteratively, starting with basic keyword matching, then add LLM integration for complex queries. Testing with real data ensured accuracy. Now, step 5, which is feature engineering and analytics. To derive insights, I created feature engineering.py file. This computes advanced metrics like patient risk scores and site performance indices. The logic traverses the graph to aggregate data using Cipher for efficiency. For instance, calculating a site's aging index, evolving, querying visits dates, and flagging delays. Techniques include vectorized operation with pandas for speed and custom formulas for domain specific calculation. Now, moving towards the API layer and integration. Finally, the API ties it all together in the backend API main.py using FastAPI. I defined endpoints like API-patients and API converse. The logic validates, requests, executes graph queries, and returns JSON responses. I added middleware for CORS, authentication, and rate limiting. Integration with the database happens via backend slash database slash init.py, which provides a connection singleton. Testing with rigorous test slash test API.py covers endpoints, while test slash test underscore graph underscore integrity.py validates data consistency. Now I would like to give you the summary of the major files, which is the for configuration I have used settings.py in the config, and for the schemas I have used dataset underscore schemas.py, and for ingestion I have used graph underscore ingestion.py file, and for agents I have used coding agent, site liaison agent, reconciliation agent, which is the rex agent, and for conversational engine I have used engine.py and rag traceability.py for the rag features, and for the feature engineering I have used feature engineering.py file, and at last for the API I have used main.py, and for database integration I have used neo4j database.py file, and for the testing there are separate test files which I have used in this project. Building the backend taught me the power of modular design, rigorous testing, and domain expertise. Technique like graph database for relationships, RAG for trustworthy AI, and agent-based systems for automation are scalable and applicable beyond healthcare. This system not only solves real problems but does so compliantly and efficiently. Thank you.
start with the processing of the front-end files. So here we can see in the API authentication folder, there are apps which contains analytics, chats, coding pages, CRA activity pages, page.tsx, EDRR, and etc. So let's begin by starting the application. First, we will start the backend. Now we will start the front end.
This is our landing page for NEST project. Dashboard, the central hub for comprehensive try overnight. The key features are filter by study and filter by sites, and we can choose date as well. And real-time alerts like showing critical issues which need attention, and data cleanliness provide a quick health score. And we also have query velocity, which shows the rate of new versus resolved queries. Now we will move to patient and site metrics, which shows detailed tracking of patient progression and data health. The key features include tracking active, completed, and discontinued status of patients, the cleanliness score per patient, detailed view of logging factors and specific queries. Now we will move to EDC matrix, which shows comprehensive subjective level data from EDC system with filtering and export capabilities. Now we will move to the page of data quality. Efficient query resolution is the key. We categorize queries by age distribution from 0 to 7 versus 30 plus age. So CROs knows exactly where to focus to prevent SLA breaches. These are the graphs which showing query aging distribution, query status overview. Now we will visit management, which ensures protocol compliances and timely data entry. The key features include identifies expected visits that haven't been entered. The visual analytics in which we have heat map which shows the number of patients entered on a particular day. And the compliance matrix shows analytics on visit adherence. Now we will move to laboratory data, which manage complex lab data and reconciliation. The key features include flags are expected when lab data results are missing. We can also track differences between EDC lab and lab systems, and also between sites like 52 and 16. And we also see lab data breakdown like EGFR, PLAT, and WBC, and so on. Now we will move to safety monitoring, which shows critical oversight for serious adverse effects. The SCA tracker, which shows comprehensive list of serious adverse events. Now we will move to SAE analytics, which shows severity distribution and SAE count by site. It also shows resolution matrix. And this is SRE trend over time. Now we will move to coding and reconciliation. The key features include auto-coding rate matrix, SOV distribution, uncoded terms by site. Now we will go to code drug coding, which shows standardized coding for containment medications, which also classifies which contains ATC classifications, which shows visual breakdown of drug classes like cardiovascular, musculoskeletal, and bed-forming organs. This is the coding progress over time from week 1 to week 10. Now we will go to forms and verification. Here we will track source data verification and form locking. The key features include SDV progress, monitor verification, and percentage by site. We can also see whether the form has been locked, frozen, or open states. Like this, the verification status, whether it is in progress or complete or not started yet. Now we will move to CRA activity dashboard, which optimize monitor resources and site visits. The key features include CRA performance, metrics on query resolution, and visit completion. Visit tracking includes monitoring visits like IMV, SIV, and COV scheduler. And also we can see follow-up tracker, which follows the specific data and updates here. Now we will see study reports. We can see the active study report is phase 3, in which we have 12,500 patients. Reports have been studied. Now we will see what are the studies are undergoing. Now we will move to alerts page. These are the dynamic alerts, proactive risk detection and management. As we can see, there are 86 alerts, and there are 15 alerts. When we press on acknowledge, it will go to resolve page. Then if you start resolving, then we will give solution like consult Mr. Dr. Mahesh, and the issue will be resolved. We can see that issue is resolved. And now we will move to orchestration of specialized AI workers. The key features include live status of reconciliation, coding, and linearization of agents, which give insight stream real-time AI findings with confidence scores. We can see we have a supervisor agent which checks overall data quality risks. Now we can see we have an AI chatbot where data is connected. When we ask questions like, so show me the sites with high missing visits. This the output where we trained the chatbot using the data available. Based on that, it will give answers. As we can see, this is about our next project. Thank you.